we going? Oh, ladies and gentlemen, Mason here, and I am going to start off the stream by addressing that yes, I'm just going to design a planetary gearbox from scratch. I don't know much about them. I have designed gears before, gear trains and gearboxes as well, or gearbox. I don't speak in multiple. I mean, technically, I have made gear trains, so that it is just uh, one step away from a full gearbox. I have done a gearbox design before, so this is a separate thing going to be um, separate from the project. I do this just as like some side quest, as like some wind down, instead of doing the main thing, because it is very toxic on the brain right now, and I don't want to do the simulink. Yeah. So before step downs in RPM. I have even designed so I'm not a complete beginner in this area. I will do close this. Yes, exit. So, oh, this is the sun gear. These are the planet gears, and this is the pinion rack ring gear, they call it actually. I mean, it is a pinion rack, but it is a ring, so it is a ring gear. So yes, we have a central sun gear, planetary gears or planet gears, and a carrier that connects the planetary gear, planet gears. Yes. Sun gear. This looks pretty nice. Yeah, this looks pretty advanced. This is the outside. Yes, and this is even a beveled version, as I see. Very cool. So carrier, which is, yeah, this is the sun. This is the carrier, planet. Aha. And we connect the ring. Oh, I think that's why, because we can either take the planets rotation, which is not much more than the sun. It is kind of similar in terms, but if we take the sun to the ring, that is going to be a lot more, because then, but also then the planets don't rotate and they are fixed to the thing. I know that either the planets spin around the sun and the outside is stationary, or the planets are stationary and pinned, and then the outside moves, and then it is taking out the thing. Yeah. Epicyclic. So yes, epi. I guess that's the center. Gearbox is beyond ordinary spur gear design. What makes Planetary special? Core mechanics, coaxial power flow, loading sharing, coaxial. Axial is the yes, coaxial. Multiple planets share torque simultaneously, higher torque density than a simple parallel shaft gearbox. 3 degrees of freedom. Sun, ring, carrier. Fix one, drive one, take output from the third. This gives large reduction in one stage, multiple ratios without extra gears, compact symmetric layouts. Kinetics must be correct first. For a simple planetary, omega sun minus the carrier, this divided by the ring versus the carrier, and that gives us the z, which is the teeth number, and that is the omega is the speed. All ratios derived from this set. Get sign conventions right. Directions. Ratio limits per stage. Practical. Sun fixed, ring input, then that it is speed up, because if the high goes to low, then this spins relatively low amount, but this will spin a lot, but then the torque will be reduced. Common reducer, yes. Carrier output. Sun fixed, ring input, carrier output. Yes, sun fixed. Okay. Common reducer. Ring fixed. I is the I think that's the is the ratio +1. Ring fixed, sun input, carrier output. Similar magnitude, opposite power flow. Typical stage ratios 3:1, 10:1. For higher ratios, stack stages, compound, planetary or serial stages. Tooth count ratios in one stage. Load sharing is not automatic. Planets split load equally. In practice, printing tolerances, carrier deflection, bearing clearance, tooth profile errors. Design counter measures 3 to 4 planets, not 2. Slight radial compliance, flexible carrier arms, or floating sun. identical bearings on all planets. Avoid over constraint, don't hard fix everything. One planet takes more load, tooth failure first. Alright. Gear geometry rules. Specific to planetaries. Tooth count compatibility critical. The ring equals the sun plus 2 planets. For equal planet spacing, integer. If this fails, planets cannot be evenly phased. Equals planet spacing. Integer means that it is a whole number, not a split shit. Alright. Fine. Fine. Profile shift is your friend. Undercut. Improves root strength. Center distance fit when printed. Bearings and carrier design. Often underestimated. Planet bearings dominate losses and life. Rolling, yes. So bearings. Rolling bearings beat printed bushings by orders of magnitude. Carrier stiffness. Carrier stiffness matters more than tooth strength. Carrier is bending, unequal load sharing. Make carrier thick, ribbed, symmetric. Print orientation so layer lines do not see shear from torque. If I'll close this. Save the project. Close this. Close this as well. So okay, we have what? We have oh, I wanted to look at the pictures. Okay, so it's here actually 5. So if we have the carriage here, then Zager's Zager. Oh no, this is not a Zager. Or is it? It is. It is just an external, not an internal Zager. Alright. These hold the gears itself. The interesting thing is, how does this take the load? So if this is the teeth, then this teeth we want to bend the whole thing there, because this spins here, spins there. So here on the teeth there is force that's going to create us bending moment here in the shaft, because that there is like eccentricity. Because if we take a look in terms of in terms of this, when we have a teeth here, but the holding is here, then that there is this distance and this amount of force, which we can't see because it is pointing towards us in this instance, because the teeth connect. The teeth are looking towards each other. When they connect, they create a force next to each other. One creates force that pushes the other, but the other has the equal amount of force as resistance, so that he doesn't want to spin. So basically here is there is this force, and it has this amount of leverage, and we could even create like a force times leverage, because how is it or is it fuck? No, yeah, this is the moment, and the other thing is that if it is a beveled gear just like this, it is going to also have a force depending on if it is left or right teeth. Then depending on that, it will have an axial force as well, which is and truly right in terms of this will be the leverage here, but or this will be the leverage for that, and I really like this picture. This is actually better than the one that I have. This looks pretty cool. This looks pretty damn cool, like so. I think this looks pretty darn good. Alright, so bearings are important as well. Stiffness matters more than teeth strength. Lost sources, planetaries, sliding at tooth contacts, especially sun to planet, sliding, sun to planet, sun to planet, sun to planet, sun to planet, sliding, bearing losses times the number of planets, churning if enclosed. What is churning? Expect per stage good alignment and bearings. Printed gears may be lower unless well finished. Printing specific guidance, yes, per G, PA, CF, PA, which is carbon fiber reinforced polyamide or polyamide. PLA only for light duty low temp. This is dog shit. I wouldn't even throw this into the trash because it is dangerous for catching fire, but other than that, PLA is just overrated. It's useless completely. So what I will do is tooth form standard involute, okay, increase module slightly, stronger roots, add generous fillets at tooth root, backlash, intentionally add 0.1 0.3 mm backlash, printer dependent. Planetaries hate zero backlash binding, as well as like it will be easier to assemble the whole thing. Internal teeth print best with higher layer resolution. Consider splitting rings into two halves for print quality. Splitting rings into two halves. Maybe I will have to. I wanna test out the new printer. Bad. What is this? Hot plate, whatever. Thermal and wear reality. Heat builds fast, multiple meshes. where oxalates if misaligned, mitigations grease compatible plastic, PTF is silicone, vent holes or metal hub inserts, lower surface speed if possible, surface speed, validation steps before committing, kinematics, sanity checks, signs and ratios, tooth compatibility, equations, worst case planet load, assume one planet takes 40-50%, carrier deflection estimate, print tolerance stack up, spin test unloaded, then incremental torque, mental model to keep, structural systems first, gear set second, carrier flex, bearing misalignment, unequal planet loading, not tooth bending stress. Module tooth counts. I was thinking about not using actual gears but using PTFE Teflon tubing and cutting it up into rings and then inserting them into kind of like and making bushings out of it so that I would be able to use that. Yeah, sure, it would be more probably higher resistance and friction than the bearings, the roller bearings, but this is much more DIY friendly and cheap solution that I would want to do. Also, I have my Ender 3 version 1 Pro here, which has the standard I think it is 220 millimeters by 220 millimeters by 250 millimeters on the Z dimensions. I was thinking that, let's say I have a motor, a car HVAC motor, which can pick up like 100 watts of power, I think, or maybe even more, 120 watts, can run at that for continuously, and it is, let's say, spinning at 3000 revolutions per minute, so 3k RPM. What would be a realistic ratio that I could step it down to in one set of gear, so one stage of gears? Could I do a 1 to 10, so I could step down the rotation from 3000 to 300, so that would be 5 per second if I'm correct. Yes. So yeah, how do we start? Because we would need to design it, because probably the torque isn't that high. Yeah, the torque is probably not going to be high, so the 3D print will probably bear it. Maybe heat. I would want to make it from PETG. I despise PLA. I have oath that I will not buy any PLA in the future because they are overpriced and I don't like them because they are mechanically just inferior to PETG. Yeah. Polylactic acid, fucking dog shit 3D printing material. Oh fuck. Motor numbers first. So the ratio this question is grounded. Each motor can deliver 100-120 watts at 3k. Torque at that operating point is 314-ish radian per sec. And that gives us 0.38 newton meters of torque. So a 10 to 1 would put it to 3.8, but probably because of bearing and all that kind of shit losses, we would have at, I mean, around 2.7. Torque level for many DIY mechanics, but it will expose friction heat issues quickly if alignment is off. 2.7. Is 1 to 10 realistic in a single stage? Yes, but it's the upper end for a single simple planetary stage if you want to be reliable when 3D printed. Reducer, arrange ring fix, sun input, carrier output. To get I10 you need a 9Z, so teeth ratio of 9. Planetary geometric constraints. To ZP, ZS, ZR. So ZR, this we would have a 12, which is very low. 108. Check spacing between the planets. 32 integer, okay. Catch: a 12-tooth sun is prone to undercut unless you profile shift or accept weaker teeth. For printing it can still work if you go slightly larger module and keep loads reasonable. Tiny sun, better print friendly approach is often 2 stages, 4 to 1, 3 to 1, so it's 12, because each stage has less extreme tooth counts and run cooler. Okay. Will it fit? Ring pitch diameter is approximately, so with the module 5 we could get a comfy tight, once you include ring thickness, housing likely too big. I like this one, Planetary GearBox. I have seen this and I like this one. This looks pretty well, pretty good. It's pretty shitty. Why is this dog so bad? Oh, yes. This website might be unsafe. Marcus save, shut up. More VPN. These are actually put into the thing. Carriage. Aha. This looks pretty nice. So basically we would need, how the fuck do we would make this? So we would have the same design wise, so we would have like a this kind of jump, and then we would be able to sit the whole ring inside, and then we would make to the last sun, and the carriage would propel this, or either the sun. Maybe this is the input, and yes, this is basically fixed, so the ring cannot spin, and then these but we would double the fucking we would double the amount of friction, because we would put in these things, and then they would be maybe yeah, I would need an insert. I would need to make an insert for this so that the neither the shaft. Ooh, how the fuck do we make this? I would need to make like bushings. Unfortunately, if you take the thing, then you can throw. Because the problem, we'll just throw a bit. So if we have this planetary gear, so this is the hole, and here you can imagine that here are the gears. It looks pretty shit, but you get the point. Here, if you put this, and here you would put the shaft of this would be this, not the sun, this is the planet, so planet gear, PG, and we would put the shaft here under the Teflon. Then basically, I'm thinking that maybe this could work with the Teflon only. Maybe. Maybe. I would need to make like a zigger, kind of like that they have done here with this. So basically would have the bushing in, and at the end I would make a zigger, 3-print a zigger, which wouldn't need to bear the whole load, just it would stop the thing from spinning off, so the shaft wouldn't fall out. Would make these ziggers probably like 3mm thick, so would have plenty of room for them so that they wouldn't fall off and wouldn't break off. So yeah, they would be 3 to 4mm thick, because it is what is this called, plastic, not fucking steel. And then we would put these here, and yeah, the bushings would be in, so they wouldn't be able to come out because of the zigger would seal the whole thing, so they wouldn't be able to axially spin out this or the other way. I mean, the other way they wouldn't be able to because the zigger holds them, but they would be able to move. I would probably would need to put another zigger, but then they would spin. Or if maybe the shaft, I don't know if I would make this a pin which is fixed, and then yeah, maybe that would be the case. So we would make this so that there is a pin, and the pin goes into the hub of this shit. I'm not going to draw it out, it's just going to be here. They usually sign it or so. This is the teeth actually. So actually here we would put this is the shaft, and basically it would continue here. I mean, I don't know why I did put this here, delete this, right? And then we continue, we add the little rim here for the zigger, and then we delete this as well. Doink. Yes, we put that there. Alright, here would go the zigger, which would be sitting in here so that the whole thing doesn't fall down. Sure, it would be smaller here, so this is not too proportional, but you get the point. And there would be the Teflon tubing inside here that would sit on here, but I don't know how I could fix this. Maybe I would put the Teflon, make the Teflon. I mean, I don't think I would need to how is that, 30 something millimeters, because it is 8 millimeters, 8 by 3, 24. I think that's even still big. So I could, if I cut the tube, because this is like a Teflon tube, I think that is 8 millimeters outside diameter and 6 in the inside, I think. And basically if I cut it open, then we would have like a roll of thing that basically we make this is the diameters, and this we can cut as long as we want, or I mean sort of. So basically this is going to be the new diameter, this side, which goes onto the pin, and this the OG diameters wise, which is this length, which we would just roll out. That is going to be 24-ish, so I even have oh, I'm just laggy for some reason, getting DDoSed. Alright, hello. Okay, so yeah, we would put the Ziegler here. We'll put the other Ziegler here. Oopsie. So that it would not be able to slide out, but other than that it wouldn't be, and then it could spin on the thing. Although the other interesting thing is, how the fuck do you keep this here? Because this would want to slide off as well, right? The gear itself would want to spin off. Or you could technically make the other alternative, which is that you don't do this, but you somehow maybe hammer in the pin. Basically you make it out of 2 pieces, and yeah, you make it out of 2 pieces, and then I don't like that, honestly. I'm not going to lie, cause but then it is still, yeah. The problem is that because this is printed like this, which is fine, and it is good actually, rather than being printed like this because it would break. But the problem is that the pin will want to break like so, because the force will come here, and if the layers are here like so, then it is easier to break than if they are like so. So we would want to make the pin like that, I mean, which would make the pin a bit less eccentric and more like a key like this. But I guess rather have a key than have like a broken axle. So maybe we'll want to make the hole like so, and hammer this pin in so that we would be fixed on that. And then we would not put these things here, but we would actually put, because this will yes, this will be here, we would put this here, and we would put this into the carriage. But then again, I don't know what would keep it there so that it wouldn't, I mean, technically what would keep it there if we have the good old straight tooths or straight teeth, it would technically want to self-align, which means that it would want to pull itself back to the track rather than fall out of the track, which means that it should be relatively at the same position, so it wouldn't need to move too much, so it wouldn't fall off the thing, hopefully. So we would put a one pin here and another pin here, and we would do the same thing, but here that the I mean it would be close to it, and it would be here the shit, the hole there. This would be the carriage actually, and it would hold the thing, and it would be the two things, these things there. It would be here, these ziggers, and then this would be the Teflon, this would be the PTFE, and that would be the carriage. Right, fine, I guess. Is this shit still working? Yeah, I think the streaming program is died or some shit. Is this fucking great of it. So whatever. Let's do this. Which is this? $1.5. Yeah, either the two. This is the inner. This is not going to fit. 1.5 or 175. Because I think the module bushing stack use steel pin shaft for each planet, smooth rod or bolt shank, rigid housing, thrust washer. Maybe we would put Teflon there as well. That could work. I'm unable to look at the things right now because the streaming program died. Whatever. All the thrust washers. I'm just reading about them now, so to collect some data in order for me to be able to start designing them tomorrow. And I have figured out that I would want to do like a 1.75 millimeter. I will need to make a word for that as well. Whatever. So, blank document, and this is going to be called burner. I mean, I will need to add more. Browse. Hate this fucking shit. Where the fuck are we? Yes. So, we would want to do something like this. Yes, we would want a M, which is a modulus of 1.75, and we would want the two stages. Both are two stages. Both are 4 to 1, 4 to 1, 4 to 1, 4 to 1. So we would reduce, but that is all right. both 4 to 1. If I design one stage, then the other is just easy, just repeating the whole thing, which is basically just Ctrl-C, Ctrl-V, full brain dead. So yes, we need to do a 4 to 1. Yes, the other thing is that we want to axial shaft support with Teflon tooling. Yes, PTF is bushing instead of bearings, workable design around creep heat. PTF is low friction but creeps under load. It will cold flow and loosen all eyes. Has lower stiffness than bearing solution. Can run hot if misaligned or too tight. If you go PTF bushings, do this makes it succeed. Bushing stack. Pin shaft, yeah, for each. PTF it was slow, but back it with a rigid housing, yes. Thrust washers. Don't press fit PTF it wirelessly and for free rotation with slide play. Build backlash interviews. PTF is silicon type, dry PTF and still can heat up at speed. Module. Print hot air, slow air with enough perimeters. Keep friction down, alignment, lubrication, because PEG softens earlier than people expect if it's constantly warm. Minimal steps. Reliability, do 2 stages, 4 to 1. So basically this is basically it. Yes, this is the thing. So basically if I want new live script. So ZR equals ZS plus 2 times ZP. Seems we need, I hope I do have the library. Which do we want? ZR integer planet spacing. Yes. Int equals ZR minus ZS. Fuck you, bitch. Divided by NP, which is the what is NP? planets or number of planets. Okay. We use NP. Let's see. We use 3 planets. We use 3 planets and clean 10 to 1. Sun. I think 17 is the minimum. So we want like 21 is not a good number. I think 17 is a good number. So ZS, which is the planet, ZP is the planet, ZR, which is the ring, S is the... What? Why the fuck? ZP, ZR, ZS, ZR, ZS, Sun, planet, ring. Where the fuck is the planet? Oh, here. The planet and the Sun. Sun is the smallest. He needs to be like at least 17, but probably like 19. Let's say 19, because that's like a good number. Then he has like a I mean, we could use his calculations. So if I mean, I can talk. So if I want to make a 4 to 1 reduction, then or like basically have a given amount of rotation, let's say the 3000, then pass it through 2 slowdowners, basically take the RPM and quote it first and then quote it again, which would give us a 16 times slow rate, which would increase the torque by 16 times, sure, times the efficiency. But yeah, I was thinking that we could do the sun gear till I would say 19 with the teeth number, and use planets as 3, so 3 planets will be module chooses like a 1.75, and I'm still thinking about the pins that whether I want to. Maybe I could buy some pins, we'll see. Yeah. What numbers do we have to go then with in terms of planets and the ring? Yes, must hold. Planet. 4 to 1. Yes, the I is the yeah, okay. So that is yes. 3 ZS. So the ring is the sun times that, which is, if we have this 3 times the sun, which is 19, then 3 times 19, fuck you, that's like 57, and the ZS combined with the geometry, ZS plus ZP, ZS equals 2ZS 2ZP, so ZP is ZS. So we're exactly 4.4 to 1. In this configuration you need planet teeth equal to sun teeth. If you want 19, then you need the 19 planet, which violates the 3 planet spacing rule because ZP must be divisible for 3 planets. Oh. For 19 teeth sun. 2 clean paths. For exact 4 to 1, with 3 planets you need divisible by 3, which would be like 21 or something, alright? 18 or 21, which would give the ring to a 72. This is a bigger one. So ZPZ, this is 24. These are very printable. 18 is usually fine if you are not making the module tiny. Keep run sun 19, change planet count to allow. Then for exact you need ZP19. So choose 2 planets, 19 planets, nonsense. Yeah, nonsense. So yeah, this is out of the window. So we will need a 21 or 24. I think I will go with the 21. That's 63 teeth. NP3 module 175 is 5 is fine. 18 or 21 if you want bigger diameter. Very solid. The default is sun 18, planet 18, ring 54, planets 3. Yes, avoid the small 12 sun, that's bullshit. Quick size check. 54 teeth with 175 module. OD. Odd wall thickness. Tooth underarm still comfortably. Maybe with a what up with the. If we do it with the bigger one, the 21, which would give us $63, and we have a 2 module, which is better because it prints out a nicer tooth geometry. 126, which is very comfy still. This is the internal. So yes, by 2 it still works fine, and then we add meat to it, which would be like 20 millimeters on both sides, which is 40, so 166. That's still comfy, still very comfy. I think I want to go with the 21 teeth. Yeah, 21 teeth and then up the module to 2, so that way the teeth profile is going to be bigger and it's going to be more accurate with the printer, and it will still fit if I give it like 20 millimeters on each side of meat on top of the you know, as the material, as the ring material. So if I calculated that's something like 2 times 63 plus 40, because 20 on each side, that's 166 millimeters of diameter even, so that still fits comfy. The time has come. Where the fuck are you? Huh? Whatever. RR, the radius of the ring, 63. Pitch diameter, okay. This is very small, actually. This is very small. Very small. I will have to see. I don't like this music. We'll see. We'll see about this. We'll make the key soft thing tomorrow. Ring root diameter smaller than the pitch diameter. Ring outside diameter pitch. M2 standard full depth tooth height is on the order of a few millimeters, not 20. 20 is mostly housing stiffness, which is fine. Alright. Yes. Why the fuck can't you do it? Whatever. All right. Internal ring must be round. Consider printing ring in a way that avoids warping. Don't skimp. Carrier flex skills loads sharing. Okay. 100 idle torque multiplication 16 minus efficiency. Yes. planet pin diameter 6 to 8 mil, planet face width 10 to 15 mil. I would go with 10. I don't want it to be too thick. Carrier thickness 10 to 6 to 10 mil with ribs. That's a lot, but I suppose it is necessary. We'll see, and we'll create the things tomorrow. The how do you say this? The CAD files. So otherwise, thanks for watching. If you tuned in for today, if you watch this later, thanks again. Do the hard work, especially when you don't feel like it. See you in the